Okay, guys, so we are back with the next section, and we're still relating angles and arcs here, but now we're going to turn our attention to a couple different kinds that we haven't seen before. So far, let's talk about what we've done so far. We have worked with central angles. So we know a central angle is an angle whose vertex is at the center, and that angle is equal to the arc. We have also worked with inscribed. So that's, let me redo that center there. So an inscribed angle made up of chords. And in that case, the angle equals half its arc. And I stress to you guys that not just the name inscribed angle, but the importance of the inscribed angle is that the vertex is on the circle. Because today we're going to see some angles that the vertex is on the circle. They're not called inscribed angles, but they're going to work the exact same way. So let's get into it. Today we're talking about angles that are formed by secants and tangents. So let's just remind ourselves what these things are. I'm going to stick to this right here. So a tangent touches the circle at exactly one spot. A secant cuts through the circle, intersecting at two places. So we can see even in the inscribed example, we're using the chords of two secants. So if we think about this as two secants, the inscribed angle is formed by those chords. But in this case, in that example, the vertex was on the circle. We're not always going to have it on the circle. Okay, so we want to look at two new scenarios. Well, let's get into that. And again, the importance is always, where is the vertex? Is the vertex at the center? Is the vertex on the circle? Or in the situations that we're going to see today, somewhere inside, somewhere outside. So let's take a look at that and see how it looks going forward. So in this example, we have a tangent and a secant, and they intersect each other, creating an angle whose vertex is on the circle. Now, since it's on the circle, we're going to use the exact same formula as we did with inscribed. This is not an inscribed angle, but we're going to use the same formula. Angle equals half its arc. So let's take a quick look at this and see what's going on. In our example here, we're talking about angle RDC and its arc. Remember, the arc always lives inside the circle. So this looks a little weird, but that's the pairing of the angle and the arc. And we're going to say that the angle in red is equal to half of the arc in red. We can flip it around and look at it from the other side too. Angle SDC and its arc. So the green angle, angle SDC, is equal to half of the green arc, arc DAC. So think about what we have going on here. We have two angles that are supplementary. So that's written in blue. And then we also have two arcs that total 360. So I marked that in the gray, the silver, whatever it looks like to you. So color coding a few of the notes here. So we have angle RDC and its arc in red. We have angle SDC and its arc in green. And then we have the idea that the two angles are supplementary because they're a linear pair, and the two arcs have to form the full circle, 360. So again, we can see the angles are half of the arcs. So we can see this shown to us in a few different ways. Now let's keep in mind, these are not inscribed angles by definition, but they work the exact same way. Whenever the angle is on the circle, the vertex is on the circle, the angle will equals half of its arc. Let's look at another example here. Here we have an angle formed by two secants, or we can say by two chords. So we're only focusing on the part of the picture that's inside the circle, but the reality is this is just a secant and another secant. So we have an angle formed, or several angles formed by two secants. Specifically, we're focusing on the chords, the parts inside the circle. And we have a formula that goes with that. The angle equals 1/2 of the sum of its arc and its vertical angles arc. It's the average. So let's take a closer look here at this example. If we want to focus on angle RDC, so RDC is right here. This angle, we're going to use its arc, RC, and its vertical angles arc, BS. So that's what we're using here. The angle, its arc, and its vertical angles arc. And it is the average of those two. If we wanted to look in the other direction, we can say angle BDR would be the average of BR and SC. Okay, so again, we're defining those relationships, the location of the angle, the location of the vertex tells us what formula to use. That's going to give us, and then we're defining the relationship. What are the parts that go into the formula? Geometry is all about the parts. Okay. And again, we'll do an example or two, but just so we can see how it applies. And now, let's see, we have angles that live outside the circle. So here, we're formed by two secants, but they intersect somewhere outside the circle. So our vertex is on the outside. Well, the inside said to add the arcs. Here, we're going to subtract the arcs. And again, the arcs. The arcs always live inside the angle. So if the angle is angle RDB, or we can say angle CDS, it cut off two arcs from that circle. And those are the two arcs we're going to use. So for our angle, we're going to subtract those two arcs. And I'm always going to say it's big arc minus its little arc, so that way we don't have to get into negative numbers and worrying about that. Always subtract the little one from the big one. And the big one is the one farther away. Look at those two arcs. This arc certainly looks bigger. And it is. So it's always the one that's farther away is the big one. Okay. So we want to be comfortable with these formulas so that we can start to apply them. Which formula we use depends on where the angle is located, and then how we substitute into the formula is simply the parts of the picture. And again, if it's not the right mixture of parts, meaning angles and arcs, then it just means that there's more than one step, and we have to apply our independent thought process to work through that. So here's a little summary And this is a really, really important slide because it covers the last few weeks of our notes. We have 4 different kinds of angles that we're dealing with in relating angles and arcs in circles. And it always depends where is the angle. So it's the location of the angle, meaning its vertex. So we always care, where does the angle live? From that, we will know what formula to use. So identify where is the vertex, and that will tell us what formula to use. Then we plug in the parts, and maybe there's more than one step. We just have to look at each problem independently. So we're not going to do every practice problem here, but we can certainly look at a couple. So let's see. Let's take a look at this first one. And I don't know why it printed that way. We're looking for angle 1. So watch. Find angle 1. It is on the circle, so we're looking for the vertex. So that tells us we're going to use angle equals half its arc. Well, its arc is right here. We don't know its arc. So this just means that there's more than one step. We can do this a couple different ways. Option 1, 360 minus 248. So let's grab our calculator and subtract that out. 360 minus 248, and you guys are doing this with me, and we get 112. That's the arc, because 360 is the whole circle, and we know that this arc is 248. So now we know that that arc is 112. Well, angle equals half of 112, and we get angle 1 equals 56 degrees. We can approach this a second way. So again, option 2. Since we know this arc is 248, we can find its angle right here. So angle equals half of 248. And that's going to tell us that angle right there equals 124. But that's not the angle we were looking for. We want its supplement. So now we're going to do 180 minus 124 to get angle 1. And that's going to tell us that angle 1 equals 56 degrees. So we've got 2 different approaches in this because it's a 2-step problem. That's all it is. We use the arc to get the angle, but it's not the angle we wanted, so there's another step. It's supplement. Or we can switch to the arc that we wanted and then get the angle that we wanted. If it's not the correct set of parts, it means there's more than one step. That's all it means. Let's take a look at the next one next to it. So again, we're looking for angle 1. I'm going to find it. And I'm always going to look for, where is the vertex? Well, since the vertex is on the inside, but not at the center, we're going to say angle equals half its arc plus vertical angles arc. So its arc, vertical angles arc. So angle 1 equals 1/2 140 plus 116. And of course we can work that out. So grab your calculator, and we have 140 plus 116. We're going to total that and cut it in half for 128. Okay. Let's see what else we have over here. Here's a good example. We have an angle on the outside. So let's check it out. Find the angle. Its location is on the outside. So we have 1/2. Angle equals 1/2. Its big arc minus its small arc. Small, little, doesn't matter. So find the two arcs inside of it. Angle 1 equals 1/2. Its big arc is 108 minus its little arc, which is 34. So 108 minus 34. We're going to cut that in half, and we get angle 1 equals 37 degrees. Okay. Let's look at one more here. Looking at number 7, again, find the angle. It's on the outside. So we need its arc and its little arc and its big arc. So look what happened here. Look at this example where we have tangents. So we touch the circle in those two spots. Now look how we broke up the red circle. This arc is 243, but we weren't given that arc. Well, we're good enough. We know that. The whole circle is 360. The big arc there is 243. So real quick, we're going to subtract that, and we're going to get 117 for that little arc. So there we go. Angle 1 equals 1/2 its big arc minus its little arc. So we had to find its little arc first, but we're going to go back to the things we already know. Tangents touch the circle at one spot, so we have two tangents. We broke the circle into two arcs, the major arc of 243 and the minor arc of 117. So those are the things that we want to observe. So let's see what else is happening. Number 8 is just like number 5, so I'm going to leave that one for you. Now, number 9 is very similar, but let's take a quick look because there is a little bit of a difference. So again, find the angle. Angle 1 would use, think about it, angle 1 is going to use the arcs, its arc, and its vertical angles arc. But we don't have either of them. So this is a good example of we don't have the right parts to pull it together. So we have to work with what we have. We have 53 and we have 41. Those are opposite arcs. So we're going to have to find that angle right there. Think about it. If we were asked to find that angle, no problem. We would use the 53 and the 41. Well, we have the 53 and the 41, so that's the angle we have to find. So angle equals 1/2 53 plus 41. And that angle, again, we grab our calculator real quick. 53 plus 41 divided by 2 is 47. Now this angle right here, that is not the angle we wanted. But these two angles together are supplementary. They're 180. So all we have to do is say 47 plus angle 1 equals 180. And now it's going to be very easy to get angle 1 because it's just 180 minus the 47. So we get 133 degrees. So because of the arcs that we were given, we had to find the angle next to the one we really wanted. It wasn't ideal, but it was what we had to do. So that's what we did. We found the angle next to the one we wanted, and then we switched over to the other one because they're supplementary. Okay? It just means there's more than one step. We can work it out. Okay, let's see what else we have here. Well, in these questions, rather than looking for the angle, we're looking for something else in the formula. But that doesn't mean that it works any differently. So think about in number 13, and I'm just going to kind of give a little advice. In number 13, the first thing we have to do, since we're going to work with x and 35, the first thing we have to do is find that angle that pairs with them. Remember, geometry is all about what parts work together. That's our problem-solving skill. So the first thing we're going to have to do is find that angle. Then we can set up the formula. In number 14, very straightforward. Our angle is on the outside. So we're going to use our outside formula. Remember, it's big arc minus little arc. So 24 equals 1/2 118 minus x. And then, of course, we do a little algebra. Number 15 is exactly the same as number 13. So again, we'd have to find that little angle first. So 180 minus 129. And that's going to give us 51 degrees for that angle. And now we know 51 equals 1/2 35 plus x. Okay. And if we look at the last three, we can see they're really all the exact same problem. Their angles are on the outside. So just like in 14, we're going to do the outside angle formula. So angle equals 1/2, and then we have to do its big arc. So its big arc is 10x plus 1 minus its little arc, which is 5x minus 1. So we have to be careful with our order of operations. Make sure that we distribute that negative sign. Those are algebraic concerns. From a geometry perspective, we know where the angle is, we pick the correct formula, and we plug in the parts. How we substitute it, we have to rely on our algebra to make sure that we don't make little mistakes. So guys, that kind of wraps up our angles and arcs unit. We had central angles, inscribed angles, and now we have angles that might be somewhere inside or somewhere outside. So again, always go back to the formula slide, and I'll scroll to it real quick. The one slide I gave you all the formulas that you're going to need for all the angles that we're using right now. So always focus on where the location of the angle is, pick the formula, and then focus on the parts. All right, guys, we're going to work on this for a day or two with varying examples. So refer back to this video over the course of a couple days so that you get the practice on it. But we're going to just vary the level of algebra, the complexity of the picture. It's all going to come down to these four formulas. All right, guys, hope everyone's doing well, and we're going to call it a wrap on this video.